Chapter 5 is on rational and radical functions. The first cluster is going to be on specifically the rational functions. The radical functions are going to be in cluster 2. So let's get started with our rational functions. We're going to begin with functions defined by y equals k over x, and we're going to talk about the domain and range of that type of function. We're going to talk about the vertical and horizontal asymptotes of that kind of function, and we're going to sketch some graphs and properties of the graphs of that kind of function. So starting off, we have our situation here talking about speed limit and time and distance. And the speed limit on the New York State Thruway is 65 miles per hour. So if you maintain an average speed of 65 miles per hour, how long will it take you to make a 200-mile trip? So since we know that distance is equal to rate times time, if we take this equation and solve for time, we would divide both sides by rate, right, to solve for time. And that would give us the new equation over here, distance divided by rate equals time. So we want to solve for time. We'll call time t. In this particular case, since we know the distance is going to be 200, and we know that the speed, the rate, is going to be 65, then 200 divided by 65 gives us 3.077. And then this would be in hours, because when you divide miles by miles per hour, the miles cancel and the units are going to flip back to hours for the time. Okay, so we're going to do something similar. We're going to complete this table where the output is going to be time and the input is going to be speed. So we're going to be changing the speeds. We had 65 as our speed in the last example. We're going to be changing our speeds to r, and then we're going to be looking at all of these over a 200-mile trip. So it's going to be 200 divided by, and then we'll do by 20, and so on. So 200 divided by 20, that gives us 10. So if you were driving for 200 miles at 20 miles per hour, take you 10 hours. At a speed of 30, it'd be 6.67 or 6.7 hours. Speed of 40, it'd be 5 hours. Speed of 50, it'd be 4 hours. Speed of 60, it'd be 3.3 hours. Speed of 70, it'd be 2.9 hours. And a speed of 80, it would be 2.5 hours. So again, each of those was computed by taking 200 and dividing it by the speeds and computing the time. Write the equation that defines time as a function of rate. So time as a function of rate is going to be the distance, which is in our case here 200, divided by r. And that is the formula that we used as we were computing each of these values. We took our 200 divided by 20, 200 divided by 30, so the 200 was on top of the division there. Okay, so as our average speed increases, what happens to the travel time? So our travel time is decreasing, but it's also decreasing by a decreasing amount. It's not decreasing at a constant rate. So the time decreases at a decreasing rate, meaning that they're getting closer together as rate increases. And what does this mean in practical terms? So in practical terms, this means that the faster you drive, the quicker you get to your destination. Okay. Now, the next situation at the bottom of the page, we have during a winter storm. We're still trying to complete that 200-mile trip here, but our speeds, our rates got drastically reduced to 10 miles per hour, 7 miles per hour, all the way down to 1 mile per hour. We want to see what happens here in terms of the speeds. So we're going to take our 200 divided by 10. I'm just sticking this into decimals, and I don't have it shown, but 200 divided by 10 is going to be 20. 200 divided by 7 is going to be 28.57 or 28.6. 200 divided by 5 is 40. 2 divided by 3 is 66.67, or I don't have room to write all the decimal places, so that's why I'm writing it to one place, since there's not enough room in these little tables here. And then divided by 2 is 100, and 200 divided by 1 is 200. So as the average speed gets closer to 0, what happens to the total travel time? The travel time increases. And it increases more and more rapidly, so at an increasing rate, because they're getting further and further apart. So increases at an increasing rate. As the rate decreases. And then in terms of a practical meaning right here, the slower you drive, the longer it's going to take to get to your destination. Oops, that one wasn't visible. The slower you drive, the longer it takes to get to your destination. Okay, now we've seen functions before that have had properties where they increase at an increasing rate or decrease at a decreasing rate. This one does both, and that's something new to our function categories than what we've seen before. It does both under different circumstances. Okay, so let's go ahead and talk about what inputs can be used, and we'll get to a sketch of this function. So remembering that our function is t of r equals 200 divided by r, they want to know if 0 can be used as an input value. So t of 0 would have us plug 0 in for r, and I'm not going to be allowed to do that because of the 0 in the denominator. We're not allowed to have a 0 in the denominator of a fraction. So can 0 be used as an input value? The answer is going to be no. And the reason is because that 0 in the denominator causes our computation to be undefined. Okay, so the practical domain. It is possible to plug negative values into this context, but they're not really going to make sense in context. We can't drive at a negative rate. So we're going to start with 0 being the lowest value, but 0 itself is no good. I'm still going to put 0 in the first position, but I'm going to put a parenthesis around it to signify that 0 itself is not included. With that parenthesis around the 0, it means up to 0, so maybe up to 0.5 miles per hour. We already had a 1 plugged in, so we could go a little smaller than 1. It's say 0.5 or 0.75 miles per hour. So 0 is the actual lower limit here. It is not included because I cannot actually plug 0 in. So the parentheses there. Up until, well, the speed limit was 65, so we're not going to push it crazy high, like into 100 for a speed. We don't want to get pulled over, so we could go maybe 65 as a top if that's what you're comfortable with. Or you could go, I don't know, people are going to go like 10 over. If they were feeling really risky about it, they could go whatever. Some kind of something along the lines of a reasonable speed for a road. 65 might be the top out right here, or 75 or something like that. So, everybody gets past if they're going the speed limit. So somebody's out there is going at maybe 75. We'll just say that at the top. Okay. All right. And again, you can have a various other speed here. I did put a bracket on this one to signify this bracket means that this number itself may be okay. And then all the way between these two, but not including the 0. Okay. Now sketch graph. Okay. So when I sketch this function, let me move my decimals graph over here. I have my function. And what I notice immediately is that there are two separate pieces to this function. There's this curve on the left-hand side, and there's this curve on the right-hand side. If I'm sketching the function over the practical domain, I'm just going to see this side of it right here. Okay. And I'll try to draw like a quick picture of that. I'm going to draw both sides. Well, I think eventually it's going to have us draw both sides in the next page. So on the practical domain, I'll draw just this side of it. So let me draw in my y-axis and my x-axis as well. So I'll note in my picture, that's just the right-hand side of the graph. In my picture, I'm just going to note that there is another piece of it down here, but this piece is not part of the practical domain. So in terms of the context of the situation, that's more of the type of the function that we would be seeing. What are the horizontal and vertical intercepts of the graph? So the intercepts would be places where I cross the x-axis or the y-axis, and there are not any. I do not cross the x-axis or the y-axis. We're getting really, really close to both of them. When we get really, really close to both of them, remember that's an asymptote. So describe the relationship between the horizontal axis, t equals 0, this axis, and the graph that our values get very large. So the function or the outputs, so we'll just say the function's outputs get close to 0. Looking at this segment right here, they get close to 0 as r gets very large. And when that happens, we know that we have a horizontal asymptote. Now, this happens on both sides of this particular graph. They're focusing on the very large, but you could talk about very large positive or very large negative. So very large negative, we also approach 0 from this side. We're getting closer and closer towards 0 from below and closer and closer towards 0 from above, depending on if we're looking at very large positive or very large negative. So it can be very large in a positive direction or very large in a negative direction, but both of those are true on this one, and we have that horizontal asymptote at the line t equals 0, or y equals 0, since that would be the equation for the x-axis there. Okay, next, describe the relationship between the vertical axis, which is r equals 0, or x equals 0 in a general case, and the graph of the function as the input values get closer to 0. So as r, which is input, gets close to 0, the output values get larger and larger. Okay, so as r gets close to 0, the output values get larger and larger. And that also happens as r gets close to 0 negative. They get larger and larger negative. Okay, and so that's going to be our vertical asymptote. And so our vertical asymptote is going to be r equals 0. And again, this is going to occur because the y values become very large positive or very large negative as the x values pinch in towards that a value. The a value in our case was, of course, 0. Okay, so we're going to use the graph that we made to approximate your average speed. Next, if the 200-mile trip takes 5 hours, okay, so that's a time. That's going to be an output. So that would be my output is 5 equals, my book up a tiny bit there, output of 5 equals 200 divided by r. And it wants us to use the graph to approximate this. So we're going to graph an output value of 5. So we'll do a y equals 5 here, and we'll intersect. Looks like it's going to take us 40 hours. So if we graph this, our intersection happens over here at 40, 5. So, sorry, 40 is the speed, not the number of hours. 5 is the number of hours. So at 40 miles per hour, it would take 5 hours. All right. Now, there's no second solution to this because I am going to be entirely below the x-axis on this side. The only time I am above the x-axis is over here on the right. And it's a continually decreasing function, so it's never going to pump back up and hit 40 again. There's only one intersection point, so one solution to that equation. Okay, so this gives us one example of a context where a rational function is useful. Now we're going to take a look a little more generally at some of our rational functions. We're going to look next at these three functions. We're going to look at f of x equals 1 over x, g of x equals 5 over x, and h of x equals 10 over x. And then we want to talk about the domains of those functions. So we're going to look at the example 1 functions and discuss their domains. So let me go ahead and clear my graph, and I'll get those graphed, and I'll pull this up after I see the functions. So first one is 1 over x. Second one is 5 over x. And the third one is 10 over x. Okay, so those are some interesting shapes. What I see about these is that the 1 over x is the innermost. The 5 over x, what happened here is that the output values, each output value got a little bit higher. So for 1, the output value, if I can find 1 somewhere in there, here, I will just do an x equals 1 line to see it. The output value was at 1, the output value is at 5, and the output value, the other one's up here at 10. So it's making the output value larger when you have a larger number on the top. You're getting a larger output for each of the inputs. So it's getting taller and a little further away from the origin because my values are a little larger. So kind of cool set of 3 shapes there. And they're going to ask me the domain. Let me pull the book down so I can see my questions, my pictures. So all 3 of these functions have the same domain. I can plug in negative numbers. I can plug in positive numbers. What I cannot plug in is 0. So all of them do eventually get really, really close to the y-axis here. It takes a tiny bit longer for the outermost function to get there, but it's minuscule compared to the entire span. It takes not very long, right? You can see that they are kind of merging together after not too much distance, and any value is acceptable for the input except for 0. So there's 2 ways that we could write this domain. One of those would just be to say that x cannot be equal to 0. X can be anything except for 0. X cannot be equal to 0. Or we could do an interval notation and say that we could use the interval from negative infinity up to 0, union the interval from 0 up to infinity. And again, that's any number, negative up to 0, not including 0, any number from 0 up to infinity. So these 2 things express the same thing. I would probably use the x not equal to 0 notation on this one just because it's easier to write. It takes less symbols. But sometimes interval notation is also useful in recognizing that anything positive and negative can be plugged into the function. So keep in mind both notations for this one. Okay, got to complete a table. So I'm going to have some assistance here with my decimals in table form. And we're going to do an f of x1. Going to do another one for g of x1 and h of x1, and I don't need my graphs right now, so I can get this table to autofill with negative 20, negative 10, negative 5, and so on. Okay, and then I'm going to fill in these values in my book. I'm going to pause after I finish typing them all and just write them down, and then we'll be able to compare. So if you want to pause after you get them in, here I can see them all. Just take a minute to jot those values down. Okay, so I've got my values written. Let me move decimals out of my way, and I drew my picture. Roughly what we were seeing on screen here for this picture. So one of the things that I noticed about this that is interesting is the symmetry. I can see that the values on the negative portion match the values on the negative input portion, match the values in the positive input portion. It's just the negative inputs have negative outputs, and the positive inputs have positive outputs. So I do see a little bit of symmetry around my vertical asymptote. I just X'd out these values because they're undefined. They can't plug 0 into the function, and that's where the vertical asymptote is. Okay, let's take a look at the next page. Using the table and graphs from problem 11, answer each of the following questions. What happens to the y values as the x values increase in magnitude indefinitely in both positive and negative directions? So if I get larger and larger inputs, the outputs get smaller and smaller, and that happens in both directions. So as the x values increase, the y values decrease towards 0. Don't want to just say decrease because that could be like 3, 2, 1. I want them to decrease towards 0. Right. So it's the horizontal asymptote for each graph. Well, the horizontal asymptote is going to be y equals 0. Y values decrease towards 0. They don't actually hit 0. So y equals 0 is the lower boundary, the asymptote for this graph. All right, and then what happens to the y values as the x values get closer to 0? So we can see that as we get closer to 0, the outputs are starting to get larger. Okay, so as the x values get closer to 0, the y values get larger. And what happens again to the y values as the x values get the negative x values get closer to 0? So same idea, but looking at it from the other side, we're getting larger negative. So the y values get larger positive. I guess I'll quantify over here. Positive, and then the y values get larger negative over here. Now, technically, the larger the negative, the smaller the number, but the magnitude, the size of the number is what I'm talking about when I'm talking about it getting larger. So they're going to be larger negative numbers. The magnitude of the number is getting larger. And so what's the vertical asymptote? Well, the x value is getting closer to 0. That's the number that's approaching 0. So x equals 0 is the vertical asymptote for those three graphs. Do the graphs have x or y intercepts? No, they do not, because the x-axis and the y-axis are both asymptotes. You're not going to be crossing them in these situations. Do the functions have a minimum value or a maximum value? No, they don't. And if I swing my Desmos graph over here again, we're going to notice that each of these graphs is strictly decreasing. Starting on the left-hand side, we're going down, we're decreasing, then there's a jump, and we continue the trend of decreasing. So these ones are decreasing only, decreasing, two separate decreasing segments. So these functions are strictly decreasing. You might be able to imagine that if you had a negative coefficient in the numerator, maybe your function would be strictly increasing. That didn't happen in these three, but hey, maybe it's going to happen in this next one. Okay. So I'm going to swap my function f of x to negative 1 over x, and then I can fill in my table here. So negative 1 over negative 10 is 0.1, then 0.2, then positive 1, 2, 10, and undefined for 0. Then when I plug in 1, I get negative 10, negative 2, negative 1, negative 0.2, and negative 0.1. Okay. Sketch the graph of Q on the first grid. Okay. So let's move my Desmos graph over. Here we go. I'm going to turn off my data plots. There we go. As you can see, instead of being in the upper right and lower left, now we're in the upper left and lower right, or quadrants 2 and 4 instead of quadrants 1 and 3. So we're in quadrant 2 and quadrant 4. Okay, so quick sketch. I'm going to draw in axes. And my sketch is going to show that my graph looks similar to what we previously experienced, but it's in different quadrants because of the negative coefficient. Part C asks us to draw the f of x equals 1 over x. So I'm going to remove the negative just to see that function. And again, that's in the quadrants 1 and 3. So we'll draw that one over here, and I'll label them as well. If the negative is not present, we see our graph representing in quadrants 1 and 3. If we see the negative, the graph represents in quadrants 2 and 4. So the first function over here, this is our q of x equals negative 1 over x. And the second graph over here is our f of x equals positive 1 over x function. Okay. And again, just another note, they didn't really mention this or ask me about this, but I can just note for myself that this function right here is increasing and increasing. This one's always increasing. rising, and then rising again. The second piece, this one's always decreasing. Just for fun. Something to think about since we mentioned always strictly decreasing above. It's the one with the negative that's always increasing. Also interesting to note. It's the one with the positive that's always decreasing. So just something to consider. Okay. Moving on to the last part, we already did our graph of f of x. Describe how the graph of negative 1 over x can be obtained from the graph of 1 over x. So it's a flip-flop across either the y-axis or the x-axis. So you have symmetry in either direction. So if you imagine flipping this across either the x or the y-axis, you would get the rotational symmetry you would need for this graph. So we can reflect f of x over either the x-axis or the y-axis to obtain the graph of q of x.